Okay, it's January 1st, 2022. Happy New Year. Well, I was sitting here watching a video, really enjoying this video. This young physicist, and she's gorgeous too. She was talking about Newton, which I really like, and I was just, everything she said made sense. I understood it, everything. And I ordered Newton's book, it's on the way. Uh, but if you see, she got all the way to here, more than 3/4 of the way. It's about 3/4 of the way through the video, and I really enjoyed the video all the way up to here. And then guess what? She mentioned Einstein, and suddenly nothing made sense. Let me play this little part here where she mentions Einstein.
GMT squared equals 4 pi squared r cubed.
This is still Newton, which makes sense. She's using his theory, his equation for gravity, which is beautiful. But then look what happens.
But there's more. I want to give you a quick peek at some really mind-boggling physics from the theory of general relativity, which is Einstein's theory that gravity can actually bend light. So when I first heard about Einstein's theory of relativity, I was like, wait, so all of that stuff I learned about Newton's laws is about gravity is wrong? And no, that's not quite true. It's just that Newton's model is not quite as precise as Einstein's model. But Newton's model is really helpful in most situations we're dealing with. What Einstein's more precise model says is this. In an earlier lesson, we said that the mass is the measure of the inertia of an object. So, for example, this cow, the mass tells us how hard we need to push it to accelerate it, F equals ma. So that's what we call the inertial mass of an object. And now we've seen that the mass of an object also determines how much gravitational traction it will be between it and other objects. So F equals gmm over r squared. The m in there is the object's gravitational mass. And when we derived little g earlier, we set those two forces equal to each other. And I did this in my physics class, and people have done it for centuries, and we canceled out the m's. But think about it for a minute. It works, but should we be able to just do that? Why are inertial and gravitational mass the same thing?
See, she questions herself. Should we be able to do that, and why are they the same thing?
Why is the m that determines inertia the same as the m that determines what gravity it feels? By the way, I didn't wonder this until after I finished my degree in physics. It's kind of a mind-blowing question.
See, she doesn't answer it either.
But enter Einstein. One of his many huge contributions to physics was an idea called the equivalence principle.
Okay, I did a video on that, number 8.
He stated that the effects of a gravitational field and the effects of accelerating motion are identical and cannot be distinguished. Whether you're sitting in your bedroom on Earth in a gravitational field, or whether aliens have kidnapped you and put you on a spaceship accelerating at 9.8 meters per second squared.
Okay, now we're talking about aliens, When we were talking about Newton, it was like down to earth, really nice stuff, man. Nice stuff that made sense. Now we're talking about aliens. So I'm going to go to this. Okay, aliens. Here's an alien. All right. So when the alien is in his spaceship, let's say he's out in space, away from gravity. So he's just floating around here in his spaceship, and his spaceship is not moving. So there's no inertia here. Let's say the spaceship is still, and he's floating around in space, okay? But then he fires up his rocket, and his ship starts, he's going to go to 1G. So he starts firing it up, and what happens is he stays still, but his rocket starts moving. Here you see. He's staying still. The rocket moves, he gets pushed up against the back wall. But as soon as he hits the wall, he starts getting inertia from the ship. All right. So now let's say the ship has reached 1g, and therefore, since he's touching the back wall here, he's at 1g too. He's at 1g also. So what happens to him? He suddenly feels like he's weightless. Okay, so it was just the pushing that uh, it's not gravity. It's inertia. It's the push, but it's a temporary thing. I don't know. It's nothing like gravity at all. I don't understand. This is like the craziest thing because gravity is um, see, he's got as soon as he reaches 1g, and the ship is constantly at 1g, it's over, and he's floating around again. But on Earth, if you want to recline on your back and watch the stars at night, um, it's constant. Gravity is constant. So, but then Einstein says, well, that's because we're constantly falling. We're constantly falling toward Earth because of the time-space grid. There's like a grid here of time and space, and uh, we're following these curves as we fall. You see, so we keep falling toward Earth. But then what if we were out in, but where's the inertia? Do you see? As soon as we hit Earth, then we would lose all the inertia from falling, and then we'd be weightless again and floating around with no inertia. You know what I mean? We would have no inertia again once we stopped falling. So, or if we're out in space and we're not moving at all, we have no inertia. What's going to cause us to follow these lines, to follow the grid towards Earth? That was never explained. So, but then Einstein said, well, the Earth is moving toward us. The Earth is moving up, and we're staying still. But then, what about somebody on the other side of Earth? Are they falling off Earth? Uh, because Earth is moving away from them. That doesn't make sense either. So then Einstein said, okay, well, he made up something else. He says, okay, we can be falling when we're not moving because of space time. And they try to explain that in one of my videos. I showed that one, how like space it's moving faster out here and slower here. So they say because the time is slower here, we're pulled down to Earth. But they don't explain why slower time would pull us toward Earth. They say that something happened. It's just, I covered in another one of my videos. It's just ridiculous. It's just ridiculous. It's ridiculous. To say that a slower time would pull us toward it without like any kind of proof. I mean, that's no answer to anything. That's just making the situation more complex. But anyway, let's see. What else did I want to say? Maybe that's it. Guess that's it. All right. Well, have a happy New Year.
You would not know. You wouldn't notice any differences in how apples fall or how heavy you feel, because in the spaceship, your apple isn't actually falling because there's no large gravitational body around to pull the apple. Imagine instead of dropping an apple, you shoot a laser beam across your bedroom. And
oh, the laser beam. Yeah, the laser beam. That's one. That's another one. That's not true either.